Hi, today we're going to continue talking about how electrons are structured in atoms. So to get us started, I've included two questions based on what you learned from our previous lesson. If you'd like to work through these on your own, go ahead, pause, do them. But I'm going to get started, reference table above my head. For oxygen, the electron configuration found on the periodic table, the Bohr notation, is 2,6. There are 8 electrons. This splits up into 1s2 and then 2s2, and then there's 4 more electrons left, so those would fall into the 2p sublevel, giving us answer D. For the second question, which one of these could not work, is disallowed, it's this 3 here in front of the S indicates that this is impossible because you cannot fit more than 2 electrons into an S sublevel. For today, we're going to subdivide things even further. So up in the upper right-hand corner, I'm not sure if you've ever noticed this walking out on the street, being out at night. There are sometimes lamps you'll see on the road that are got this yellow color to it. And almost always these specific yellow lamps contain low pressure sodium, elemental sodium, really low pressure to keep it a gas. And that gas is being excited like the gas discharge tubes we've seen before. This sodium is used, these lamps are well known and have been used for a long time because of their very bright, very distinctive yellow color, and it works to light up, things at night. When you look at the spectrum, though, when you get a really good instrument to really subdivide those lines and see specifically where they are, you'll notice on this graph that that yellow light is actually 2 lines of very, very, very close wavelength. Except on here, it's just labeled as 590. So why are there 2 lines when it's just labeled as 590? And the short answer is that the individual orbitals in the sublevels can sometimes behave slightly differently based on how the electrons are occupying them. And so that's where we have to go today. We have to talk about how individual electrons fill individual orbitals in sublevels, in principal energy levels, in atoms. So just as a brief review, here's the same table from before. Here are your sublevels, the number of orbitals and the number of electrons. We can now establish the rule, and moving forward, that it's a hard rule, the end. This is one where there's no exceptions. Every orbital can only hold up to 2 electrons, and that's where you get the 2 in the 2n squared. So each energy level has n squared orbitals, but can hold 2n squared electrons because 2 per orbital. To talk a little bit more about that, these electrons, I want to kind of like mix this together with other things we've talked about. In the Bohr model, we said, yay, the Bohr model, it happens. And then right after that, I said, actually not yay, unyay, because it only works for hydrogen. And the reason it only works for hydrogen is that when you have 1 electron in your atom, all of the sublevel, all of the orbitals and all of the sublevels of all the principal energy levels are degenerate. And the word degenerate in this context means of the same energy. As soon as multiple electrons start occupying these orbitals, the presence of other electrons impacts any other electrons you're talking about. So first off, I'll say this. Orbitals don't really exist when they're empty. Like, we can imagine that hypothetically they would exist, but an orbital is a cloud that is only a cloud when the electron is there. So we can hypothetically know at what energy and location an orbital would exist if it were full, but it's not. It doesn't exist when it's not. So that is to say, as soon as we start getting more electrons, and these little arrows here I'm going to talk about soon are representing electrons, what ends up happening is that for other atoms than hydrogen, the extra electrons would cause this to be redrawn as more of a 2s, and then there are 3 individual 2p orbitals at different energy levels. This is why a lot of times when you look online, you'll see 2s and 2p at different energy levels, because almost always we're talking about not hydrogen. But if you were talking about hydrogen, all of those orbitals would actually be at the same energy, and that's why the Bohr model works with it without sublevels and without orbitals, because they, for all intents and purposes, are the same. So now that we've established this idea that, these sublevels have different energies, but within them there are degenerate orbitals within the sublevel. Remember, I drew the 3p sublevels, or 3p orbitals at the same energy. I want to talk a little bit about something called spin. No, the electrons are not spinning like a top. It is one of those other intrinsic characteristics of particles that are on the atomic scale. Like we know that protons, neutrons, and electrons have mass, charge, and a certain energy, right? And we talked about the energy level of electrons. But there is also this characteristic called spin. It has to do with angular momentum, magnetic angular momentum. I don't really want to get into it. The most important thing you need to know is that it can be either up or down. And we're going to draw this with these half arrows. The reason why we're drawing them with half arrows is technically the spin is a positive or negative 1/2, but that's not super important. I'm sure if you draw full arrows, it's one of those things that it's wrong, but it's not really wrong. So if you ever see full arrows, know that we're just doing these half arrows to get that point across. So for electrons, they can either be up or down, which means that two given electrons can either be spin aligned or spin misaligned. This is aligned and this is misaligned. Moving forward from there, we can start to build these orbitals a little bit. We're starting to see how these electrons are going to start to fit in these orbitals. And so this leads us, before we get too far ahead of ourselves, to the Pauli exclusion principle. Technically, the Pauli exclusion principle states that no two electrons in an atom can have the same 4 quantum numbers. We haven't talked about that, so I'm going to simplify it to say if two electrons are in the same orbital, they must have opposite spin. So in other words, this is the only way you can really draw helium in the ground state. If you have two electrons in an orbital, one's up, the other one has to be down. That's it. You cannot have two electrons of the same spin in the same orbital, in the same sublevel, in the same level, in the same atom. You ever hear that song, like, you know, there was a branch on the tree, and the tree in the hole, and the hole in the ground? Yeah, it feels like that, doesn't it? So, putting this all together, still, we have this situation where electrons can exist in these orbitals, and everything we said before is still the case. You know, this lowest energy configuration is still the lowest energy configuration, right? So like what we said about oxygen at the beginning is still true. It's 2,6, and then it's 1s2, 2s2, 2p4. We're just adding another layer to say, but how are those two organized? How are those 4 organized? If degenerate orbitals exist, we're going to say that a spin-aligned configuration is a lower energy than a spin-misaligned configuration. I'm going to add a little bit more to that, but that's basically what Hund's rule says. A spin-aligned configuration is a lower energy. So when you are filling up oxygen, it looks like this. That might make sense, might not make sense. Pause, think about what I said, rewind if you need to. But if you had, say, an empty p orbital and you put the first electron in, right? Say these electrons had feelings and hopes and dreams, and they were capable of making choices. You could say that your second electron could occupy the next orbital over, or you could say that that electron could occupy the same orbital, but in the opposite spin, right? So these two colors represent two possibilities. Between these two possibilities, I'm going to say that, as a rule, this orientation is a lower energy than this orientation. In other words, up, 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 before any downs. And as one of these general practices, too, as a convention, we always write spin up before spin down. That's just how it's done. Spin up and spin down don't really matter until you apply a magnetic field, so we were being slightly arbitrary about it, but that's how it is. This series of writing lines with arrows on them, up and down and all that, is what we call orbital notation, specifically saying which electrons are in the atom, in which orbital, in all of that structure. You can see them drawn like this, with energy increasing as you go up the y-axis and then putting degenerate orbitals on the same level. You can also see it written as we've seen oxygen below. So these two are equivalent orbital notations. And really what we're doing is we're taking the subshell notation and then splitting it up even further, applying Pauli exclusion principle and Hund's rule. See how they did the whole arrows there? Don't like it. You can use lines or you can use boxes. But just to show where this all comes from, this, if we're going up a level, this is your orbital notation. If we're going to sublevel notation and we have Bohr notation, we can like show all of them. We know the Bohr notation is 2, 4. That gets split up into 1s2, 2s2, 2p, 4. It's not 2, 4. I don't know why I keep saying it. It's 2, 6. And then the 1s2, 2s2, and 2p4 get shown that way, where you've got up, down, up, down, up, down, up, up. Technically up, 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 down, because that's the order. And you could go through this process with all of the elements, right? Like we talked about how you can translate any Bohr notation into a sublevel notation. You can translate any sublevel notation into an orbital notation. These are, of course, all ground state configurations. And I'm showing these also because you can, again, draw lines or boxes, right? For lithium, you know, you could do this instead and you label it as 1s and 2s and 2p, and then you can do this. You know, you can show that those two are equivalent. If you have degenerate orbitals and you're drawing boxes, you can have the boxes touch. Having the lines touch is confusing. If you did keep going, of course, you know, you could draw a 3D sublevel and you'd have 5 lines. The Fs would have 7, you know, or boxes. So just to wrap things up, I wanted to show some potential excited orbital notation configurations for a lithium atom. That's a lot of vocab. So here we have the ground state because this aligns with what this is all the rules we've seen so far. So we could instead have we have a P available, right? So we could do this. That could be one excited state for lithium. That would be written as, you know, 1s1, 2s1, 2p1, or 1, 2 if you're going back to the Bohr notation. It is also possible to have, I'm going to not write the labels over and over again. It's possible to have this be an excited state, and there is a slightly different energy of that excited state versus the other previous excited state. You could have one where, you know, you put both of them into the 2p, and then you could even have one, you know, obviously we can occupy the 3rd and 4th energy levels. You could have one that, you know, does that. You might wonder whether or not there's a difference between the 3rd one I've drawn and maybe one like this. Technically, these two don't really have a different energy to them. They are degenerate excited states, if that's even a thing, but then the vocabulary gets even more obnoxious, and I'd rather not go there because this is obnoxious enough. Thanks for watching.